Yeah, so we'll start with the next section in our discussion, which is about Bayesian inference. So let's go back to this motivating problem that we had. So we had this model of temperature, which is being tracked, or we are looking at temperature at every day, and we are saying that the temperature on the next day is the current day's temperature plus some increment I. And we are able to see measurements of this temperature. So we get these values Mn, which are the current temperature values plus some measurement noise terms. So in our last session, we talked about how to think about Nn. So Nn is something that we can think about as noise. I mean, it's measurement noise, which is modeled as a random variable. Okay, and this random variable, well, it's a mathematical object which is actually not just a variable, it is a function which has an associated probability mass function, which tells us what is the chance that the random variable takes a particular value if the random variable is discrete, or it has a probability density function. Okay. So what the model basically says is that, well, before you actually get to observe that particular random variable, you don't know what value it will take. So what you can do is you can make a list of all possible values that the random variable can take. Okay. And the probability density function or the probability mass function can be used to talk about the chance that the random variable takes that value. Okay. And we also saw that there are some standard distributions which can be used to specify this. For example, the normal distribution here, or in this case, we talked about this binomial distribution. Okay. So this is what we have seen. So we have basically seen how to get to a model of this NN. Okay. That is what we have. So remember that we also talked about, like when we started, we also had another question, which was how do we find I? Okay. So now we have a way to think about NN. The other question that we wanted to think about was how to find I. So how do we find I? So we briefly discussed that before. So we said that we could take the successive differences, right? So if you have Mn and Mn plus 1, right? What can you do? Like, can you do something with that? So we have Mn and Mn plus 1, then. So Mn, we think of it as Tn plus this Nn, and Mn plus 1 is Tn plus 1 plus this. So how do I find I from this? So what we are saying is Tn plus 1 is Tn plus I. Okay. So is there a way to get I from this? So we can think about subtracting, right? So we can think about subtracting. So if we subtract this from that, according to our model, what we get will be I plus this. Okay. Now, can we do something more here, or shall we say that this, whatever we get here, remember that this is the value that we can actually compute. Okay? So, shall we say that this is in fact what I is, or should we do something more? I mean, intuitively, what do you think? Like, can you suggest something more that can be done? So, this is like some kind of random noise kind of a quantity there, right? So if you are faced with this kind of a situation, what will you do? Should we do some kind of averaging? Do you think that will help? So suppose you took another measurement, mn plus 2, and you did this, then what will you get? Okay, you'll get that. So maybe you can think about summing up such differences. Okay, so if you sum up, say, k of these differences, what will you get here on this side? So you sum up k of these things. This side you will get ki plus. But these things will get like cancelled out when you sum up, right? So you might get you might get something like this, right? And then you can think about maybe dividing by k. Okay. So I mean, this is something that probably you might do, right? When you are taking measurements, you might try to average measurements, right? So I'm just writing down something here. I mean, there is right now I'm not giving any special meaning or justification for this. I'm just appealing to the fact that when you take measurements, sometimes you average it, right? So that's all that I'm doing, right? Okay. So you can do something like this, right? So this is what you have. Maybe this average you will say that this is I. Maybe you think that when you have a large enough k, this quantity will be not very large, right? So this will be approximately I, right? So that is one way that you can sort of estimate the value of I from measurements in this particular case. Okay? So this is one particular way. Let's say that this is one particular way. So what I want to illustrate is that there are, like, when you think about inference, there are possibly I mean, when you look at it, there are unconnected ways of doing inference, which are, I mean, there is some underlying theory behind all that, but when you look at it from a superficial viewpoint, they might look unconnected. So we will look at some examples just to sort of see this. And then we will try to look at this method called Bayesian inference for doing inference, or trying to get to the value of I. Okay. So let's take another example. So in this example, what we have is we have some DC voltage source here. There is some voltage source here. And we are, say, we have a resistance here, there is an ammeter here and a voltmeter here. Okay. So we are measuring the value of current through this resistance. These are ideal voltmeters and ammeters. We are trying to measure the value of current through this resistance, also measuring the voltage across the resistance. Okay. And suppose we get to see these values. So these are the measurements that we are making. We are getting to see these values. So this is the current that we see for this voltage, like that. Okay. So here, I have left out some values here. Okay. So can you tell me what those values would be? Any idea what those values would be? Sorry? Yeah, so you have to find out the resistance. If you knew the value of the resistance, then you can probably write this down, right? Okay, so here also you are using a model for the relationship between voltage and current, right? So you're using Ohm's law for that. So if you think about it, if you try to plot voltage values on this axis and current values here, okay, then this slope here tells you what the resistance is, right? So if you try to plot all these values which you already know, that means you make a point here with x coordinate equal to 0.9, sorry, 0.9 and y coordinate equal to that, okay. Sorry, the other way around. We are doing it the other way around. So if voltage is along this axis and current is along this axis, okay. So if you put 0.9 here, you get this, okay, like that. If you have all these points, and you can see that this lies along a line. It kind of looks like this lies along a line, and the slope of this line here is actually the reciprocal of resistance. Okay. So in this problem also, you are trying to do something similar to what you had done previously, right? So there you are trying to find out the value of that increment I. Here you are again trying to estimate something which is 1 by the resistance, okay, the reciprocal of this resistance. And maybe by looking at it, you kind of feel that, okay, this line here, it has a slope of 1, okay. I mean, these values look almost similar, right? So this has a slope of 1. So maybe the resistance value is 1. So the rest of the values that you have is something like this. Okay, so that is how you can predict new values for the current as a function of the voltage. Okay. So here you have kind of gone one step maybe more compared with the previous problem. So there you try to estimate the parameter. Here you have estimated a parameter which is resistance and then use that to do some prediction. Okay. You could do that in the previous case also. You could try to predict forward, try to say what the temperature is on a new day and all that. Okay, but here there is one more sort of thing that comes up. So suppose I tell you that the actual values of the current that you measure, okay, so earlier this red thing was the prediction that you made, but now the green thing is the actual values that you get to see if you really measure, okay. And these are different from your predicted values. So there is some kind of a error here. Okay. If you had a slightly different model where you also had, say, temperature values. Okay. So what happens is that when the temperature changes, okay, the resistance also changes. And suppose the way in which the resistance changes is modeled in the following way. So there is like a nominal resistance of 1 and then there is some variation due to temperature. Okay. So this is a simplified model. So suppose you had this model, okay, then your prediction would have been like perfectly correct. Okay. So this is again like one step more than what we had previously. So here we are essentially trying to look at like two different kinds of models and we are trying to say that, okay, one model is giving you a better sort of prediction compared with the other. Okay. So these are all toy problems. So in a realistic setting, even with this particular model, you may not get like, you may not get better results or things like that. It's not easy to predict those kind of things. So when you look at the ingredients of the problems that we are interested in, we will usually have data. These data will have different features or different you can think about data as a kind of a vector with different elements indicating different properties. Like in the earlier case, it was current and temperature, okay, things like that. So you have data with features and we have a model. This model will have parameters. Okay, so for example, the resistance value or the increment in temperature, these are parameters. Okay. And what we actually need is a method of choosing parameters for the model. Okay. So in this case, this is just a heuristic sort of way in which we said that we could find I. This could be one method. Okay, so there is no sort of, right now there is no theoretical basis for this. We have just written it down. But this is probably one way of choosing parameters for the model. In this example, what we did is we just plotted it so that it looks like it is lying on a line with slope 1. So therefore the parameter value was 1. Right? So that was our method of choosing parameters. Okay, and this method of choosing parameters for the model, okay, we choose it based on the data that we are seeing. Okay. So this is like the inference problem that we are looking at. Okay, and then once we have this model, we also need a way to do prediction based on the model. This is the prediction problem that we can have. And then as we just saw, you also need a way to compare models. Okay? You need to do model selection. Okay? So these are different ingredients of a problem, of a data inference problem that you would usually face. Okay? So right now what we are going to do is we are going to just concentrate on this part. That means if we have a model and if that model has certain parameters, then how do we infer those parameters from data? Okay, so that is what we will primarily concentrate on. But you should understand that there are also other things that we would like to do once we have data and we have a model. Not just inference, we have to do prediction, we have to do model selection, all those kind of things are there. So we need some framework for doing all these things, okay? Doing all these things. This is a more sort of general way in which I have stated this problem. So the kind of problems that we look at, they can be thought of as what are known as regression problems. Okay? So you basically have data. In this example, we have like two-dimensional data. And what we are trying to do is to basically build a model for one dimension of this data as a function of another dimension. Okay? And we can have different models. For example, like we can have a linear model. Okay? This is what we just saw in the previous example. The parameters of this model are the slope and intercept, which we are trying to find. Okay? And when we are talking about regression, a general way in which we find parameters is to sort of try and adjust these parameters. So we can try to change its intercept, we can try to change its slope in such a way that the error between this line that we have or this model that we have and the points are minimized. Okay? And the way that we measure error is we basically look at this distance, we take squares of these distances and we add it up and we say that that's like an error metric, and we try to adjust the slope here and the intercept here in such a way that that error metric is minimized. Okay? So in fact, many of the things that we had discussed, like for example, this method that we talked about here, okay, can be formally put in these terms. Okay? So inference can be thought of as finding parameters that minimize some kind of error metric. Okay? Once we have the model, then we can use this model for prediction. And you can also do model comparisons. Okay? Maybe model comparisons can be done using this kind of an error metric, okay? But with some modifications. So what we need is, we need a framework for doing this. We need a framework for doing inference, prediction, and model selection. And this Bayesian approach is one such framework that we can use. Okay? The other sort of framework that people usually think about is similar to what I just described. So you try to find out, or you try to formulate some error metric, like the squared error metric that we talked about, and then try to choose model parameters that minimize the squared error metric. Okay? So that is one way. And many such problems, like you can pose as optimization problems, where you try to find out this error metric, find out the parameters of the model that minimize this error metric. You can try to do that. But what we are going to do is something different. Okay? So we are trying to use this thing called Bayesian approach for doing all these things. Okay? But primarily we will concentrate on just inference. Now, why this Bayesian approach? So I will try to illustrate it using some examples. Okay? And I think these examples are, should be understandable. So suppose we do this kind of fitting. Okay? So this is probably something that you would have done. So you have some points here, and I want to find a linear function here that explains or tries to say that this value here is a linear function of this data that I have here. Okay? So this value, I try to say that it is some slope times x plus y intercept. Okay? So this is how it looks like. So in fact, if I try to choose a slope value and an intercept value in such a way that this line when I draw here, when I look at the square of this distance and if I sum it up, okay, the values that I choose here minimizes that squared error metric over all choices of this value and this value. Okay, so that is how I have chosen it. So maybe this is something that you would have done. You would have done a curve fitting, right? So this is similar to curve fitting. Okay. So suppose I do this, okay, and suppose now what happens is that I do this. I mean, I maybe take another, say, sensor, okay, and collect some other data, okay, but it is coming from the same system, but say it is collected using another sensor, which has maybe slightly different amount of noise and things like that. But when I try to fit this particular model to that data, what I get to see is that the values are different. Okay? So instead of this 22 here, I get 18. Here, instead of this 4 here, I'm getting 2.9. Okay? So each time I do these measurements and do this kind of fitting or do this kind of parameter inference, I get different values. Which one is correct? So is there a way to say that this is correct or that is correct?
We can say if we compare the results with some reference.
Suppose you don't have a reference. So you are taking measurements. Suppose you are taking measurements on different days. Okay, so maybe every day you get some data points like this. Every day you try to fit a model like that. Okay? You expect that the underlying system is like not changing from day to day, but still you are seeing that these values are different. Okay? It might come up due to the fact that there is some the measurement noise that you have, it is random. Okay? So that is why you are getting slightly different data, but you are actually getting different values for this slope and this intercept, okay, when you are doing it on different days. So which one is correct here?
Either we can do one thing, we can plot one small line. Connecting the line connecting the corners.
Line connecting the?
Lower right and upper.
Like these 2 points?
Yes, 1:1 point.
Okay.
So I will check the regression line. If it is closely matching those lines, so we can say this one is good.
What is the logic behind that? Why should you trust these 2 points more?
Actually, slope will be one. And intercept will be, yeah. So, sir, now I got one point by visualizing these two graphs. This intercept part and the slope will be very close to 1:1 line.
Okay, but suppose you do this for some other data set. Suppose it doesn't look like that. Then do you think this will happen or will not happen? So each time when you take this measurement, the measurement values change. If you do this procedure, these values will also change. Okay. Can you repeat what you are saying? Okay, error between? Okay. Mm-hmm. Okay. Okay, so let me just come to that. Okay, so anyway here, so I hope you agree that this will happen. Like when you are taking these measurements, even if you think that the underlying system has not changed, because there is noise and noise changes, when you do this kind of a procedure, this set of values that you get will change. Okay. And maybe we will look at a slightly simpler sort of example here to understand this. So here, suppose I have again a voltage source. I'm trying to measure this voltage. Okay. So when I measure this voltage, maybe I measure it using this voltmeter. Again, there is some sort of randomness in the measurement. Okay. So when I measure it 5 times, I get these values. Okay. Maybe I will report the average value here. The average value is this. But suppose I again do 5 measurements, maybe I will get these values, and the average is going to be different. Okay. Average will be different. So again, the question is which one is correct? Okay. How do you even report these values? So if we formalize this a little bit, okay, so suppose we say that the ith measurement that we have is like, the actual value say 5. Okay, the actual value of that DC source is 5. But what we measure is 5 plus some noise, and that noise is a random variable like this. Okay, noise is a random variable like this. Then, as she mentioned, one common way in which people report the value that you measure is by using something called confidence intervals. Have you come across any this before, like this term called a confidence interval? So the idea is that if you report a single value like this, okay, so this value changes. Okay, so when you take this measurement again, it changes. So one common way in which people report this is by saying that, okay, there is a range of values that you say. Maybe it is like 4.5 and 5.5. Okay, and you say that this is like the 95% confidence interval for this measurement. Okay, so I'm sort of just looking at this or going through this very superficially just to motivate why we need to go to Bayesian inference. But can you tell me what this means? Like, so suppose I say that instead of reporting a single value, I say that there is an interval of values. Maybe the actual mean lies inside this interval, right? With high probability. That is the kind of intuition that I have when I try to make this definition. But it turns out that that is actually again not true, okay? Because when if you have done this before, if you try to compute these confidence intervals are also computed based on data, okay? So usually when we say 95% confidence interval and all, the wrong interpretation that we give to it is that we think there is high probability that the actual mean that we are trying to find, or the actual voltage source value that we are trying to find, lies in this interval with high probability. That's the usual interpretation that we give, but that is actually wrong. Okay? In fact, what happens is if we compute this confidence interval again based on new data, that confidence interval will also change. Okay? So maybe it will look like this. Okay, so then you can see that this kind of a definition does not really make sense there. So these kind of problems come up in the sort of usual ways in which we do inference, like when we do inference based on mean squared error and things like that. Okay? And this is something that Bayesian inference tries to help with. It tries to help with interpretability of these results. Okay? So as we take up some examples. And there is also one more thing that Bayesian inference helps with. And again, I will take an example to explain this. So suppose you have a coin, and we talked about this coin bias before, right? So a coin is biased when you say that the probability that it comes up heads is not 50%, it is something else. Okay? So suppose you have a coin and you want to know whether a coin is fair or not. Okay? So suppose you toss this coin 10 times and you get to see these outcomes. Okay? So you see that this is heads, then 3 tails, okay, which I am saying losses, okay? And then another 5 heads. Okay? So here, do you think this coin is fair? Is there any way to say whether this coin is fair or not? So here if you look at the fraction of heads, it is like 7 out of 10. The fraction of tails is like 3 out of 10, right? So do you think whether it is fair or not? Maybe not easy to say, okay? It's not easy to say. Maybe if you look at many more such tosses, okay? Maybe you will see that the fraction of time the heads is coming up is like 0.6, the fraction of time the tails is coming up is 0.4. Okay? Do you still think the coin is fair or not? It is close to 0.5. Okay? But suppose you are also given this additional information that the coin is not from, say, a government mint. Okay? So it's not a standard coin. Okay? So suppose you are given this additional information. Does it change your inference? It should change your inference. I mean, maybe you think that somebody is trying to cheat you then if it is not a standard coin. But if you are just looking at the fraction of time that you are seeing heads or tails here, if you are just using that as a way to infer whether the coin is fair or not, that is not taking care of this information that you have. Okay? It is not taking care of this prior information that you have about the coin, which should matter in the inference. Okay? So this sort of techniques that we sort of went through before, they are not able to basically do few things which Bayesian inference is trying to solve. Okay? So these are some issues that it tries to solve. So in these methods, we don't have a very well understood way of reporting results. Okay, or they are usually misunderstood, like this thing about confidence intervals and all. People interpret them in a wrong way, but that is not the, that is something that Bayesian inference tries to solve. Okay, we will see how it is doing that. The other thing is that these kind of methods, you can think of them as not being able to incorporate prior information when you are doing inference, which again Bayesian inference will try to solve. Okay? So because of these two reasons, we are going into Bayesian inference. Okay? Because of this inability of these other methods to take into account prior information. For example, if somebody tells you that it's summer season. Okay? So how do you make use of that information in inferring this I here? In this procedure, that information is not used at all. Maybe if it is summer season, you know that this I is going to be greater than some value, right? So in this procedure, because we are just doing these subtractions and taking an average, how is that information taken care of? Is there any way to incorporate that here? So these other kind of methods don't do that, but when you come to Bayesian inference, there is a way to do it. Okay? And again, there is a way to interpret the results that you are getting in a better way when you are doing Bayesian inference. So let us try to see what this Bayesian approach is. So in this Bayesian approach, what we start out with is something called Bayesian belief. Okay? So again, we are in a scenario where we have non-deterministic things, or when we have random things which we cannot predict. But here what we do is, we say that there is a way in which we can quantify our belief in a particular statement. Okay? For example, we can believe very strongly that there is going to be rain, something like that. But we are going to quantify that. We are going to put a number to it. We are going to say that this is our belief that that will happen, or that statement is true. Okay? So this is called a Bayesian belief. So for example, like we were thinking about that measurement. So these are kinds of beliefs that you can have. So you can believe very strongly, like 100% chance that, or you have 100% belief that the value of the DC source is 5 volts. Okay? So that is a belief. Or you can believe that, okay, it is maybe not exactly 5 volts, it is between 4.5 and 5.3 volts, and maybe like all those values can be like equally likely. You can believe that. So that is like a belief that you can have. Now, in an inference problem, what happens is that you can start with what is known as a prior belief about the about the parameter that you are trying to infer, or about the model that you are trying to use. Okay? So you start with a prior belief. And in this Bayesian approach, whatever information that you have, like for example, we had this information that the coin was not from a government mint. Okay, so you will try to incorporate that information as part of this prior belief. Okay, so here for example, I mean, if you are looking at the coin bias problem, if you knew that the coin was from a government mint, you can strongly believe that the bias of the coin is 0.5. So you have 100% belief in that, and you don't believe that the bias of the coin is different from 0.5. So that's the kind of belief that you can start with. That's like your prior belief. Okay? If you think that, or if you have this information that the coin is not from a government mint, maybe you believe that the coin has either high bias or low bias. Okay? Maybe high bias of 0.9, low bias of 0.1, and you can strongly believe that. Maybe you can assign some numbers to it. So you can believe that it is 0.9, say, with belief like 0.5 and 0.1 with belief 0.5. Okay? Or you can also assign some other numbers. We will shortly see that we can use probability to talk about these beliefs. Okay? But that's what we mean by prior belief. Any questions here? Yeah, we will see it should be something like the probability. So we can use probabilities to quantify beliefs. Okay? But right now, just think about this as some number. Maybe it's a number between 0 and 1000 if you want. Okay? But you can quantify beliefs using probabilities. Okay, so this is like your so this is the prior belief. Okay, now what happens is that you will have data. Okay, so you will have data, and the data that we see will be connected with whatever we are trying to infer. Okay, we will have a model for explaining the data as a function of these underlying parameters, and because of this connection that we have between the data and the the parameters that we are trying to infer and all that, what happens is that we will be able to update our belief. Okay, so we are starting with some prior belief, then we see some data. So based on that data, we will be able to update our belief, and this is in fact what happens in inference. Okay? And this updated belief is then used for prediction and model selection and things like that, but we will only go up to this part. Okay? Now, so this is what generally happens in this Bayesian procedure. Okay? So it's all based upon these beliefs. So we start with a belief about whatever the system that we have. For example, here, right? So we can start with some belief about what this I is. Okay? For example, suppose you know that it is summer, then you can start by saying that, okay, these temperatures should probably go up. Okay? So maybe this value I here is say 1 degrees or 2 degrees. Okay? So I strongly believe that it is 1 or 2, but it is, I mean, I don't have a strong belief that it is 3. So maybe I will say that my prior belief on this I is like it is 1 degrees with a belief of say, maybe I assign a value 0.5 here. It is 2 degrees, maybe I assign a value 0.4 here, and it is 3 degrees, maybe I assign a value 0.1 here. Okay? So maybe I do something like that. And then what happens is I will see this data. So I will see these MNs, and based on this data, okay, I will try to revise these beliefs. So once I see this data, okay, so maybe somehow I was delusional and I thought that it was summer, but it was actually like winter or something like that. So when I see this data, I will have to revise my beliefs. I might see that this Mn plus 1 minus Mn is actually say negative. Okay, so that means that it is temperature is going down. Okay, so then I'll have to revise my beliefs, and there should be a way to do that. There should be some arithmetic or there should be some formula that tells me how to revise my beliefs. And when I revise these beliefs, what is happening is that I'm actually inferring something about this I. Okay, so that is the Bayesian procedure. Okay. So let us try to see how this is formalized. And it turns out that, as I said, like we need to do all these things. So we are quantifying beliefs using numbers. So when we are trying to revise these beliefs, when you are trying to change these numbers based on data, data is numeric, okay? Then how do we do all these manipulations? Okay, so do we need some kind of a new framework for doing this? Do we need a new sort of arithmetic of operating on beliefs and things like that? Okay, so that's a natural question that comes up. But luckily here, probability theory comes to the rescue. So although we won't go into this, so there is some theory that says that if you have a way of encoding beliefs using numbers, okay, and if those if that system, if that way of encoding beliefs using numbers satisfies some reasonable axioms, okay, then this Cox axiomatic approach that basically shows that you can think about beliefs as probabilities. Okay, so the way in which you quantify beliefs can be done using probability. So you can think about probabilities as your representation of belief. So your belief values, you had to put a belief on I. You can instead think about putting a probability distribution on I. Okay, and that probability distribution, it represents beliefs. Okay, it represents your belief on I. So we can basically think about the belief as given by a probability distribution. So whatever parameters that we want to infer, say in a model like this I here or the resistance that we had in the other example, so they are actually quantities which have beliefs associated with them, but because we are thinking about these beliefs as being represented using probability distributions, we basically think about these quantities as random variables. Okay? But this is just a way to infer these quantities. Okay? We have beliefs on these quantities which are represented using distributions. So they look like random variables, so we are going to think about them as random variables. Okay? So the quantities that we want to infer are now random variables with an associated distribution. So when we start out, they have a prior distribution which represents the prior belief that we have on the random variables. And then we will revise these distributions on the basis of data that we see. Okay, and these revised distributions will actually tell us something about, okay, what these values could be as a function of data that we have seen. Okay, so that is the idea. So now because we have probabilities as representing beliefs, so these are some examples of prior probabilities that you can give. Okay, for example, if you are thinking about this problem of say inferring voltage. Okay, so you are trying to infer voltage in some for that example that we had seen. So you can think that okay, so maybe this is not very clear. Okay, but what we have here is a function that looks like this. Okay, so you can say that well, I don't know exactly what that voltage will be, but I believe that that voltage is between say 4.5 and 5.5 volts or 5.3 volts, something like that. And I don't really know what value it can take even between 4.5 and 5.5. So I say that, okay, all these values are like equally likely to have happened. Okay. So suppose that voltage source is coming from a reputed manufacturer, then maybe my belief will change. So I can say that, okay, I believe that this 5 volt rated voltage supply is, okay, maybe not exactly 5 volts, but I might believe that it is going to be a value between 4.9 and 5.1 volts. So this is another prior belief that I can have. Okay. So I can represent these beliefs using these probability distributions now. Okay. Probability distributions now, which are just representations of that belief. Okay. And these are other examples. Okay, so in fact, if you have a Gaussian or a normally distributed belief, this is how the belief looks like. Okay, so here this one, right? You can see a very sharp kind of function here. So that kind of tells you that you strongly believe that whatever parameters say that you are trying to infer, you strongly believe that it is taking a value near around 1. Okay? And this second one, well, here you are more unsure, you are not very sure about what that value is. So you can say that, okay, it is, okay, maybe between -2 and 4, but you don't really know. So you give it a sort of a spread out distribution just to encode that belief that you are somewhat unsure. Maybe it is near around 1, but you are not very sure that it is concentrated at 1, right? So you use a belief like that. Okay? So these are ways in which the beliefs can be encoded using probabilities. And you can have a lot of such distributions for that, for doing this. This is another example. This is actually called a beta distribution. Okay? This is again used to, I mean, this is a sort of a standard distribution that you use in Bayesian approach to model prior beliefs on quantities which are restricted between 0 and 1. Okay? So this is another example of a prior probability. Okay, so here, let me just go back here. So as I said, this is the sort of approach that we have. So we have Bayesian belief that encodes, and I mean, we have this notion of Bayesian belief which is represented using probabilities. When we start out, we use a prior belief. Now we have seen that a prior belief is representable using a distribution like this. So we have that. Now, what do we do next? So we observe data and then we have to update our belief. Now the question is, how do we update our belief based on observed data? Okay? So doing this is based upon a rule in probability which is called the Bayes rule. Okay? So let us try to understand what this Bayes rule is. So we will try to understand it in terms of discrete random variables, but almost the same kind of formulae or relationships will hold for continuous random variables also. So let's look at this case where x and y are two discrete random variables. Okay? So there are two discrete random variables. Now we can define this conditional probability of x given y. Okay? So what was conditional probability? So it's like you see the value of one random variable and then you try to ask, okay, what is the distribution of the other random variable given that you have observed something, right? Given that you have observed this value for this first random variable. Okay. Now this conditional probability, this probability of x equal to x, y equal to y, given y equal to y, you can write it as probability of x equal to x and probability of y equal to y given, divided by this probability. Okay, so why is this true? So again, this has to do with like, I mean, you can think about the random variable taking a value as an event. Okay, so this is like the event that you have a given b. Okay, this is another event. The random variable y has taken the value small y. And we saw that probability of a given b is like probability of ab divided by probability of b. Right? So this is basically a consequence of the conditional probability definition that we had for events. Okay? We are just now using random variables to talk about the same thing. Okay? Now, what Bayes rule does is that it tries to put this in a slightly different way. Okay? So you have probability of x given y as probability of x and y divided by probability of y. It just tries to express this probability of xy in this way. How do we get this? This numerator here. So we get the numerator here from a similar sort of expression as this, where you have y here and x here, right? So if you look at probability of y equal to y given x equal to x, so that is probability of x and y divided by probability of x equal to x. You just take that probability to the other side, you will get this numerator. Okay. So you have probability of x given y equal to y, okay, equal to probability of x equal to x into probability of y given x divided by probability of y. Okay. So this is what the Bayes rule is. We will take up some examples to understand this better. Okay. And you can also express the Bayes rule in a different way. Like if you look at this denominator here, this is probability of y equal to y. This probability of y equal to y can be written using the total probability rule. We had studied this total probability rule before, like this. Okay. So here, the important thing to understand is that if you look at the events that x takes a value, say x1, and another event that x takes the value x2, then those two are disjoint events. Okay. Why is that? Because remember that x is like a map, right? So you have the sample space, you have the real line. So x is like a map. So we are looking at one set of points in the sample space, which is an event, such that x has taken the value small x1. We are looking at another set of outcomes or points in the sample space such that x has taken the value x2. Now these two cannot have shared elements, right? That cannot happen. I mean, by definition, we are saying that all the points here have mapped to this value x2, and by definition, all these points here are mapped to this value x1. So there cannot be an intersection here. So they are disjoint. So these are disjoint sets that you have. Okay? And the total probability rule, like if you go back and look at it, it basically says that you can write probability of, in our notation it was probability of B is equal to summation of probability of some AI into probability of B given AI. Right? So this is the same thing that we have here. So this is Bayes rule. So we have sort of seen this in a very abstract way. Okay? Let us try to see how we can use this. Okay? Let's try to see how we can use this. So we will first take up a numerical example to understand the mechanics of doing this, and then we will see how it is used. So let's take two random variables x and y, and suppose this is the joint distribution of x and y. That means this is the probability of x equal to x and y equal to y. So what this table says is that if you have x and y, then this, say, let's look at this entry here. This is the probability that x takes the value 2 and y takes the value 2. That's what this table says. Different elements of this table or this matrix gives you this probability. Okay? So can you find this out? What is probability of x equal to 1 given y equal to 3? How is it possible to find this out? I mean, can you do that from this table? So probability of x equal to 1 given y equal to 3 is the probability of x equal to 1 and y equal to 3 divided by the probability of y, right? Okay, probability of y equal to 3. So probability of x equal to 1 and y equal to 3, what is that? So you can read that off from the table. So x equal to 1, x equal to 1 and y equal to 3, right? So that is 0.05. Okay, so that you get from this. How do you find probability of y equal to 3? So probability of y equal to 3, you basically get from the total probability rule. Okay, so there are three sort of disjoint sets that you have. Okay, which you get by looking at these different values that x can take. Okay? So x equal to 1 and y equal to 3 is disjoint from x equal to 2 and y equal to 3, disjoint from x equal to 3 and y equal to 3. They are all mutually disjoint. So you can use total probability rule and get that the probability of y is the sum of these three quantities here. So that is 0.05 plus 0.2 plus 0.1. Okay, so you get that. So the probability of x equal to 1 given y equal to 3 is, just take this ratio, so you'll get 1 by, what is that, 1 by 7. Okay, so you get that. Okay, so we have found this out. Now, this is not Bayes rule, we have just found out the conditional probability. So, right, we have just find out probability of y equal to 1 given, x equal to 1 given y equal to 3. So what Bayes rule tells us is that we can find this out in a different way, right? So what Bayes rule tells us is that instead of looking at probability of x equal to 1 given y equal to 3, you can actually change the conditioning, you can change whatever event that you are conditioning on and still find out this probability, right? So what Bayes rule says is that this is equal to probability of x equal to 1 into probability of y equal to 3 given x is equal to 1. So it's the opposite of whatever we are doing, whatever we wanted here, okay? Divided by probability of y. That's what Bayes rule is, right? This is what Bayes rule is. So we found this out from the table directly, and now we are just trying to see whether Bayes rule gives us the same answer. Okay? So this is just mechanical, we are just trying and see how this formula can be used. Okay? So if you look at the right hand side of the Bayes rule, so that's what we are doing now. So you look at probability of x equal to 1 into probability of y equal to 3 given x equal to 1. So this is the opposite of what we had here. And that again we can find out from this table. Okay? So the probability of x equal to 1, again using total probability rule you can find that. It will be the probability of x equal to 1, right? Yeah, so you have to go back here, yeah, x equal to 1. So if you sum it up, it will be 0.1 plus 0.1, so that will be 0.2. So we have that, and then probability of y equal to 3 given x equal to 1. How do we find that? Well, we again have to do the definition of conditional probability here to find it. So probability of x equal to 3 given x is equal to 1 is, sorry, probability of y equal to 3 given x is equal to 1 is probability of y equal to 3 and x is equal to 1, which is 0.05, right? So that is this 0.05 divided by what? Probability of x is equal to 1, right? So that will give you, okay, why am I getting 0.25, is that correct? This is 0.2, the other one was 0.05, right? Yeah, right. So that will be 0.25, right? 0.05 divided by 0.2, right? So 0.5 by 2, so that will be 0.25. So I'll get 0.05 here. Okay. So let me just write it down. So we are trying to just do Bayes rule. So this one. So this we computed. Bayes rule says that this is the same as this. Okay. So we have now computed this. This is 0.2, this is 0.25. Okay. So that is the numerator. So we get it as 0.05. And we also want to now find this out, probability of y equal to 3. Okay. So where do we get that from? So we had already found it before when we did this. Okay. So we can either put that here and try to get it. Or what we can do is we can try to use this version of Bayes rule where we had this in the denominator. Okay. So the good thing about this is that it has similar looking terms in both numerator and denominator. Okay. So we can maybe try to use that. So then again, like when you do this, we will get that is 0.35. Okay. So that is 0.35, and when you take the ratio of this with that 0.35, you get 1 by 7. Okay. So this is just mechanical. We are just trying to sort of put down these quantities on both left hand side and right hand side of the Bayes rule and try to show that they match. Okay. That's all. Any questions here? When you're talking of discrete events? When we are talking about discrete random variables, when we are talking about things like this, the events that the random variable takes one particular value, then that event will be disjoint from any other event, like which says x is equal to some other value. That is true. Okay, so I mean, for example, you have a version of Bayes rule for events. Like you have two events, right? So if you have probability of A and B, then you can always write it as probability of AB by probability of B, and then you can always write this as probability of say, so you're trying to do this, right? So probability of A into probability of B given A, probability of B. So this does not depend on any disjoint property of A and B. Or if you want to write it in like that, okay. So there, like if you, I mean, suppose you have, I mean, one simple way to do this is you look at something like this. So this is A complement. Okay. We can do that. Okay. And there are versions of this, for example, suppose you start out with some set of disjoint sets AI, okay, some set of disjoint sets AI, then you can have a version of this rule that looks like this. Here again, you use total probability rule to write down probability of B in the denominator. Okay. Yeah. So this is the general version. Like, so there is no. I mean, here in this version, of course, you need the AIs to be disjoint. Okay. But you don't really need. I mean, in general, you can use the other rule. So that doesn't say anything about whether something is disjoint or not. Okay, so this is Bayes rule. Any questions here? Okay, so yeah. Sorry, come again. Yeah, you're talking about this example. Okay. Yeah, so in fact, so we'll see that. So when we're talking about Bayesian inference, we are not really trying to get to a single value for I. So in fact, in its basic form, what we finally end up with is a distribution on I. Yes, and then there are ways to summarize that. So then you will see that, okay, maybe you want like a single value to describe that distribution. That single value will be the expectation. So that we saw earlier, right? So if you have a distribution, there are ways to summarize the distribution. So the expectation is a way to summarize it. So you can get the distribution and then say that, okay, the expected value of this is this much. Okay, so that's a way to get a single value estimate. There are also other things that you can do. Okay, so this is Bayes rule. So we have just understood the formula now. So let us try to apply it to a simple problem to try and understand how to exactly do this Bayesian inference. Okay. So this is again the problem that I briefly mentioned before. So I have a coin. I don't know whether the coin is biased or not, so I'm trying to find that out. Okay. And when I toss the coin, this is what I get. Okay. So I have heads, and then okay, loss means tails, and then heads again. Now here, okay, let us try to see how we will go about inferring the bias. So this theta here that I have, let me think about that as the bias of my coin. So theta is like the probability that I have that the coin comes up heads. Okay? Theta is the probability that the coin comes up heads. Now, if I think about each of these coin tosses as being independent of one another, okay, so the event that the coin comes up heads in the first toss is independent of whatever happens in the second toss, independent of whatever happens again and again, then the probability that, okay, I get to see a particular value for the number of heads, given that my bias is some value theta, is going to be like this in this particular case. Okay. Why this formula is because, so you see that there is this theta coming here, right? Theta raised to 7. That is because in each time there is a probability theta of the coin coming up heads. And in this particular thing that we have observed, we have seen heads 7 times. Now, because we are assuming that these are all independent, you can take the product of these probabilities, okay, and you can write it as theta raised to 7. Okay, so that is how this theta raised to 7 comes up here. You also have tails coming up 3 times. So if the probability of heads is theta, the probability of tails is going to be 1 minus theta. So given that the bias is theta, the probability that you have actually seen 7 heads is going to be something like this. Okay, it is this. Is everyone clear about that? Okay. So this is the probability that y equal to y given theta. So here this small y is actually 7. You can write this for any y. Okay? So in fact, if y is the number of heads that you have seen, it will be like theta raised to y into 1 minus theta raised to 10 minus y. Okay? That's how it will look like in general. Now, okay, so I start with this inference problem. So what I do is I start with a prior belief on my theta. Okay, so I am going to believe that my theta is either 0.4 or 0.5 or 0.6. Okay, and these are the beliefs that I associate with it. So here, what I'm doing is I'm actually giving sort of more belief to the fact that it is fair. So I'm saying that I believe like 0.6 with a belief of 0.6 that it is 0.5, only 0.2 for 0.4 and 0.2 for 0.6. So this is my belief. Okay, this is the prior belief that I have. Okay, any questions here? Okay, so now what is the so I'm trying to use Bayes rule. So I'm trying to use Bayes rule to update my beliefs. Okay? Now, what do I mean by an updated belief? By an updated belief, what I mean is just this conditional probability. Okay? So, given that you have seen data, what is the new distribution I have over theta? That is my updated belief. Okay? So remember that in the Bayesian procedure that we set down, there are these steps, right? So we start with the prior belief, we see data, and then we update our belief, right? So what is that updated belief? That updated belief is just this conditional probability. Okay? And it is very natural, like, I mean, that you talk about a conditional probability here to think about this updated belief, right? So given that you have seen data, what is the new distribution that you have? That is your updated belief. Okay? These updated beliefs are also called posterior beliefs or posterior distributions. Okay? So you start with a prior distribution, you see data, and then you get a posterior distribution. Now, because this is in the form of this conditional distribution, what we are going to do is we are going to compute this using Bayes rule. So Bayes rule is the formula that we use for updating our beliefs, okay, in this Bayesian procedure. So we want to find probability of theta equal to 0.4 given that y equal to y, whatever we have observed. So how do we compute that? So we can compute it using Bayes rule. You can see what is being done here. So what is this 0.2? So this is actually the probability that theta was 0.4, okay, into the probability of y given theta. So that is this. So if theta were 0.4, the probability of y given theta, which is this, will have that specific value of theta substituted in it. So that is this. That's why this 0.4 is coming here. And you are computing this probability divided by probability of y. And probability of y, you again compute using that summation, the total probability rule which we had. So that you can compute and you will see that it is 0.07. Probability of theta equal to 0.5. Again, you start with the prior probability of theta, so that is 0.6 into the probability of y given this 7 given that theta is 0.5. So you can again compute it, that is 0.58 in this case, and like that, likewise. So you do it for the last probability also. So what you can see here is something nice. Like, see, we started out with this prior belief that, okay, I kind of think it is fair, it is like 0.6. There is a belief of 0.6 that it is 0.5, that the bias is 0.5. I also had some belief on 0.4 and 0.6. I've actually observed a sequence of coin tosses in which there were more heads. So intuitively, what do we think? We think that the belief on these two values should sort of maybe go up, okay? But this belief on 0.4 should come down, right? So we are getting, or we are seeing more heads. So we kind of have to revise our belief now. Our intuition is that the belief that we have on values of the bias which are over 0.5 should maybe go up. The belief on values of bias which are less than 0.5 should go down, and that is actually happening here, right? That is actually happening here. So the Bayesian update, that is the procedure of revising our beliefs on the basis of data and the prior belief that we have, is based on Bayes rule, okay? So this is an example which sort of shows that. Any questions here? Yes, so the denominator is, this is probability of y, that is the same.
So can we omit that, or is it just a scaling factor, or does it have?
Right, so it is, yeah, actually when you do, maybe when you do this numerically, it is a factor that you can omit. So you can, I mean, even if you don't compute it, you can actually do this. Yes, so yeah, so it's like a normalization factor. Otherwise, these things won't add up to 1. I mean, this is again a probability, right? So these probabilities should add up to 1. So this probability of y equal to y is a normalization factor which does that. But when you are, say, doing it, I mean, there are methods to do it on a computer via simulations and things like that. So when you do that, you don't really need to compute this. There are ways to do it without computing the normalization. Okay, so this is, yeah, this is basically Bayes rule applied to this problem of inference. Okay. Yeah, any other questions? Okay, so this is just a sort of a diagram to again reinforce the steps that we have. So what we actually want to find is this. This is the revised belief, which is called the posterior. So what Bayes rule tells us is this, okay? And in Bayesian inference, the usual terminology that we use for these quantities are like this. So you have a posterior, which is the revised belief that we have. That is the product of the prior, okay, which is what we start out with this function here. Okay. This is the probability of seeing some data given that your parameter, like the coin bias here, has taken some value. This is called the likelihood function. This is called the likelihood function. This actually comes from whatever model that you have, which you are using to explain the data as a function of your underlying parameters. Okay? So that's what you have there. And this quantity that you have, the probability of y equal to y, this is called the evidence, okay, in Bayesian terminology. So this is the update step. So once you have this update step, you end up with this revised estimate, or I should say revised distribution, the posterior distribution for the quantity that you are trying to infer. Okay, so I will just try to sort of show you some examples, but these are, I won't be able to show you how these are computed, but let me just show you how it is, how the results come about. Okay, so this is the problem that we were talking about before. Like we had that unknown voltage that we wanted to compute, right? So that is this problem. So we had like a source here. We were trying to measure this voltage here. Okay. So here, think about theta as this voltage. Okay, that this whatever battery or whatever that we have here. Think about theta as the voltage corresponding to that. So when we start out, we don't know anything about what this voltage is. So we assume a prior on this. Okay, so we say that the voltage can be anywhere between 4.5 and 5.5 volts. Okay, but we don't really know. So we say it's going to be like equally likely any value between these. So we are encoding that as this prior distribution, which again looks like this. Now, what happens is that we will get data. Okay? Like we saw the data that we had seen before, right? We get tables of this data. Now, with this data, okay, so for example, suppose we measure a value 6.5532. Okay, suppose we measure that value. Okay, sorry, I think there is some typo there. It shouldn't be 6 point, maybe it's like 4 point. No, let it be something like 5.3, okay, not 6.5. Okay? So suppose we have a value like 5.3. So we measure that data. Now what happens is that this prior belief that we had will get updated, okay, will get updated into a new distribution that might look like this. Okay? So it looks something like that now. So you can see that because we have seen a higher value, so this value is, let's say it's around 5.3 or something like that, the distribution now looks sort of skewed. It is now saying that there is more belief that the value is like more than 5 compared with a value which is less than 5. Okay? So the distribution will look skewed like that. When you get additional values, your posterior will keep changing. Okay? And finally, like when you collect enough sort of data, you will see that your posterior might end up looking something like this. Okay? So this is the sort of core object that you get after the Bayesian inference procedure. You get the posterior distribution from which you can say something about what that value would be, okay? What that voltage source's value would be. Okay? For example, this is the final distribution that I get. Okay? This is the final distribution that I get. I can think about taking the mean of this distribution or the expectation of this distribution and then report it as a single value. Okay? And that single value is, I have to say that is the expected value of my posterior distribution. That's a single value estimate of the voltage, because that is one thing I can do. Or I can look at the value of voltage here that has the maximum probability, okay? Or that has the maximum belief. So that also is something that I can give as an estimate, but I have to specify what it is. So it's like the max belief value. That is another way. Or I can do one more thing. So I can look at an interval here, say between 4.9 and 5.1, So suppose I say that, or suppose I find that between this 4.9 and 5.1, say 95% of my belief lies. Okay, here belief is a probability. So 95% of my probability lies. Okay. This is a Bayesian interval estimate for my voltage. So I can say that this is like a high probability interval in which I believe that my actual value I lies. This is actually much more easy to interpret compared with the usual confidence interval. So when I say this is a high probability interval, what I really mean is that I believe that my actual voltage source value here lies in that interval with 95% belief or 95% probability. Okay. So that is another way in which I can give an estimate. So that's one thing I can do. So here, when we actually did it, I mean, I will maybe sort of show you a glimpse of how it is done. So what we are doing here is something like this. So we start with a prior, which is like this. The likelihood, that means the value that I measure, the voltage that I measure, is modeled as this theta plus Gaussian noise or normal noise with some mean and variance. Okay. So this is my model. This is my model. And what it actually gives us is this distribution. It gives us the distribution of V given theta, which was important, right? Because we saw that that is part of this, this procedure. So we want this. So that you can actually get from this, okay? Get from this. And that is used in these computations. Okay? So whatever I have shown here is something that I am numerically computing. It is not done by hand using some software package. Okay? And that software package will enable you to find the final distribution, okay? The posterior distribution. There is one more important thing here, which is that I have shown you two or three steps of this procedure. So I have started out with a prior. I have gotten a single value, I have observed a single value, updated that prior to this posterior. Okay. Then I told you that I got another value and then still updated my posterior. Okay. So when I do this update, my prior for this update is actually this posterior. Okay. So because I have already like seen that data and I have revised my belief to this new distribution. So when I do one more step of Bayesian update, I start with my posterior itself as my prior. Okay, and then I do my update. So that is also something that is very natural when you do this Bayesian inference procedure. Okay, that when you have data and suppose data is coming in sequentially, there is a way to sort of incorporate that. So you basically do the Bayesian update step with the prior as the previous posterior. Okay, so that's what you can do here. And if you look at that other problem, the Bayesian, the coin bias problem, and this is a so we are looking at like 100 coin tosses and all. So this is like the prior that I have on the bias when I start. And then as we get data, then we will be able to revise our prior into a posterior, which looks like this. So I think in this case it was more or less, yeah. So it is biased, I think. So finally we are getting a distribution which is not around 0.5. It is around 0.7, 0.65, something like that. Okay. So this is our posterior belief. And then if we go back to our earlier problem, like we were trying to fit data to a line, right? There also you can do this. You can think about the data that we see as some AX plus B plus some noise, if you think about it like that. Here the parameters of our model are A and B. So we have to start out with a prior distribution on A and B, which we think of, say, as something like this. Okay. Then this is how our prior distribution looks like, and then we will be, this is our posterior will look like. And finally, we will be able to sort of get to the posteriors for A and B. And this is an interesting sort of visualization which shows you how the final estimate of A and B can be thought of as. So we are getting a distribution on A and B here, the slope and the intercept terms. Okay? So if we think about taking values from that posterior distribution, okay, and if we try to plot lines with that slope and intercept values coming from the posterior distribution, then we get a distribution of lines like this. Okay? This is actually this is a representation of our Bayesian estimate for that linear model that we had. Okay? In fact, we can sort of see that wherever we get sort of a dense plot here, okay, that kind of shows you that the slope and intercept are more probable, or they have more belief, leading to that more dense plots there. So that is kind of like a representation of our linear model. Okay, so what we have seen is this introduction to Bayesian approach. We have basically seen Bayes rule and how to do the Bayesian update using Bayes rule, and seen some examples of Bayesian inference. So I will just quickly sort of tell you something about how to do this in a computer and things like that. So usually when we try to compute these probabilities, okay, it will turn out that well, probability of theta is something that is given to you. It's like, or you start out with a prior. The likelihood comes from a model like this. Okay, so that's also something that you can have. Usually it will turn out that computing this denominator is hard. Okay? So it's usually like when you are looking at, say, this theta coming from some high dimensional space and things like that. If you're using total probability rule, then you see that this is like an integral which you have to do over a high dimensional space. So that's a hard problem. So computing this term is hard. Okay? So there are two ways in which we try to sort of handle this thing. So one is a more analytical way where we sort of choose some special forms for this prior probability function or the prior belief and the likelihood function. Okay? For example, if you say that the prior that you have, like here, okay, so if you say that the prior that you have is Gaussian or normally distributed, and if you also assume a model where the kind of noise that you have is Gaussian, okay, or if that likelihood function is Gaussian, then it becomes easier to do this Bayesian update, okay, because there is some formula that comes about very easily when you use Gaussian for the prior and Gaussian for the likelihood. Okay. It turns out that the posterior is also Gaussian in that case, and then if it is Gaussian, then what you have to do is to just find out the mean value and the variance of the Gaussian. Okay. Actually, when you do Kalman filtering, you will basically see that it's a consequence of this. Okay. So there are also other such functions. If you choose for the prior and the likelihood, this thing becomes easier. So these are actually called conjugate priors and likelihood. Okay, so that they are like matched in some sense, so that there is an easy way to do this Bayesian update. Okay, so this is a simpler example. So suppose you start with a likelihood for that coin bias problem. Sorry, you start with a prior for the coin bias problem, which has this particular form. Okay, so we actually started out with a discrete valued distribution, but suppose you had started out with a distribution like this. This is called a beta distribution. So if you had started out with something like that, then it actually turns out that it's very easy to go from this to the probability of theta given y. You just have to count the number of heads that you get. You can just add it here in the exponent and you can compute this posterior probability. Okay? So it becomes very easy when you do this. So there are several examples like this, Gaussian and Gaussian, this beta distribution and this particular distribution for the number of heads. These are all masked in some sense. Okay? So this is one way to do it. There are also computational techniques where what you do is you say that, okay, computing this denominator is hard, So what you actually do is you don't even compute it. Okay? You say that what you basically need is this proportionality. Okay? So you have the posterior probability proportional to this product. Okay? And then there are ways to approximate this posterior probability. One way to approximate a probability distribution is to just take samples from that distribution. So you basically take, like suppose you say that you have a coin, okay, and that coin has a bias of P. So that bias of P is the distribution. So instead of saying that distribution, instead of specifying that distribution, you can instead represent that using a sequence of coin toss values. So you just say that you have heads, 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 tails, tails, tails. So it is possible to get an estimate of that P from this sequence. You can take the fraction, long run fraction of times you have gotten a heads and use that, right? Similarly, whenever you have a distribution, instead of specifying that distribution, you can instead use samples from that distribution or values that you see from the random variable having that distribution to represent that. Okay? Now there are ways to generate samples from this distribution without this normalization factor. Okay? And in fact, the whatever I had shown, they use a software package to basically do this. So a very popular technique for doing this is called Markov chain Monte Carlo. Okay? We won't be going to that, but this is basically a technique for obtaining samples from this unnormalized posterior. So you just need to specify these two things, and this procedure will be able to generate samples from this product. Okay? And there are software packages which can do that. I don't think we'll get time for this, but I'll just show you how it can be done. Yeah, so yeah, this is basically the code that was used to generate whatever I had shown, that Bayesian voltage measurement and all that. So I'm using a package called PyMC. This is Python code. PyMC is like a software package which can be used to do this Markov chain Monte Carlo, using MCMC. It's something that you can use to do Markov chain Monte Carlo. And you can see that it is very simple to sort of set up the model here, which we are using to infer the value of the voltage. So I think it's kind of readable. So what we are saying is that there is a prior, mu is the value of the voltage. This prior is this uniform distribution. This is called a uniform distribution between 4.5 to 5.5. There is a likelihood function, which is Gaussian distributed. And you can see that its mean is mu. Okay, so that is how that dependency is coming in between the underlying parameter and whatever you're observing. And then you can just basically set up the model here using this construct, and you can take samples from the posterior. So whatever I showed you is actually the set of samples that you get from the posterior. I have shown you the distribution of those samples, okay, which is computed using what is known as a histogram. So this is very simple. So you can extend it to other cases also, like Bayesian regression, whatever we showed, and all that. Okay, so I think this is probably a good point to stop. So we won't have time to get into MCMC in detail, but you can just sort of take away the point that MCMC is used to generate samples from this posterior distribution, which we are computing using Bayes rule. Okay? So that's all. Yeah. If you have any questions?
Any questions?
While dealing with real problem
Yeah.
of data assimilation, will we always assume that our model follows Gaussian distribution in 0 and some bias associated?
Well, it is not really required. For example, this procedure, this Bayesian inference procedure, can be applied to any kind of distribution that you want, but the problem will become harder if you don't assume Gaussian.
So, to make the simplicity of our problem, we are assuming.
Yeah, because if you assume Gaussian distributions, like we talked about something here, right? If you have this prior and likelihood, if they are both Gaussian in nature, then it turns out that computing the posterior becomes easy. It is also Gaussian. So you just need some formulae that tells you like what is the mean of the new posterior as a function of the prior's mean and maybe a function of the likelihood, something like that. Actually, you will see that like when you are doing Kalman filtering, that is essentially what you are doing. Yeah, so it just simplifies the problem. You might have some analytical approaches if you assume Gaussian.
If you want to simplify that, may use some error in our real life problem. So
Yeah.
how to account those problems?
Well, okay, so
there are methods to incorporate the non-Gaussianity. For instance, he was talking about Kalman filter, but if you use particle filters, you can incorporate non-Gaussianity in it. But the issue is that we are dealing with a high-dimensional system. So the computationally, how much it is feasible is to be discussed. So that's why we basically go for Gaussian assumptions. Non-Gaussianity is possible. It is not something which is not possible, but that's going to increase our computational requirements. Okay. Any other questions? If there are no more questions, let us thank Professor Vineeth for having the excellent lectures.
yeah, I also want to mention that this particular package, right, you can actually incorporate other distributions also, non-Gaussian distributions as part of the model. That's possible. But as he mentioned, it becomes computationally harder to do it, especially in high-dimensional spaces.
Sir, will we get this slide?
Yeah, all the slides will be distributed to you. Okay, and yeah, today I don't know. I mean, we'll try to share it as early as possible.
Share the slides with
You can
them.
share the slides with me.
Yeah, it's already with them. So,
Okay, so we can break for lunch.